Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to optoelectronics devices and systems. In the previous videos we discussed about various methods of modulation of light, which is the signal carrier in optoelectronics communication system. So in the next series of videos we will be focusing our discussion on the design of the various components that are used in a typical optoelectronic communication system. So for that we have to brush our concepts related to some of the basic things, and for that it is very important to understand about semiconductors. Already we have discussed about semiconductors in detail in basic electronics and also in physics of semiconductor devices, but still just in a quick way we'll discuss these things. So why semiconductors is very important for optoelectronics? It is because the two most important components in optoelectronics communication system, the source, optoelectronic source, and the detectors, okay, the optoelectronic detector, source which generates the light and detector which detects light, the two most fundamental components in optoelectronic system, they are made up of semiconductors. So it is very important to understand semiconductors and their properties, their applications, in order to understand the functioning working principle of optoelectronics communication system. Okay, so in a quick way, what is a semiconductor? So basically so here semiconductor is a substance which has its resistivity or conductivity lying in between that of conductors and insulators, and normally it lies in between 10 to the power minus 4 to 0.5 ohm meter. Examples: silicon, germanium, selenium, they are elemental semiconductors. There are other compound semiconductors too that we'll discuss. So basically it has its conducting properties in between that of perfect conductors and perfect insulators. So the properties of semiconductor is that the same, its resistivity is less than that of an insulator but more than that of a conductor. Another important property which is very important when it comes to design of optoelectronic sensors is semiconductors, they have negative temperature coefficient of resistance. That is, the resistance of semiconductors, it increases with decrease in temperature or vice versa. So this property is exploited in sensors and transducers, semiconductor sensors and transducers. Another important property is that all semiconductors, they are crystalline in nature, okay, where all the atoms of the semiconductor, whichever we are using, it has a well defined arrangement. So if you remember, we discussed about double refraction, about the crystalline nature of the substance and how the geometry, optical axis, everything affects refraction. So that thing will also come into play. So these are the three most important properties of semiconductors, okay. Then is the classification of semiconductors. So we can classify semiconductors on the basis of two aspects: first, composition; second, doping. On the basis of composition, semiconductors can be classified as simple semiconductors and compound semiconductors. So simple semiconductors, they consist of only one element, single element. They are also called as elemental semiconductors. Example: silicon, germanium, selenium, whatever. So one element only. Compound semiconductors, they consist of more than one elements, okay. basically the combination of elements from group 3 and group 5 of the periodic table. Example, gallium arsenide, gallium phosphide, indium phosphide, aluminum gallium nitride, indium gallium nitride, like that. Okay. Then on the basis of doping, okay, so basically doping is the process of addition of foreign substances or impurities, as it is called, to enhance the conductivity of semiconductors. Okay, so on the basis of that, we can divide semiconductors as intrinsic and extrinsic semiconductors. So intrinsic semiconductors are semiconductors in their original form without any external impurity added. Semiconductors in their absolute pure state with no foreign substances added, they are intrinsic semiconductors. Extrinsic semiconductors are those where foreign substances or impurities are added by doping process to enhance their conductivity. Again, depending on the nature of impurity which is added, extrinsic semiconductors can be divided into two categories. First, N-type semiconductor, second, P-type semiconductor. So when for an N-type semiconductor, suppose we add a pentavalent impurity. What is a pentavalent impurity? An atom with 5 valence electrons, 5 electrons in the outermost orbit. For example, let's say phosphorus, arsenic, antimony, if that is used, let's say we have intrinsic silicon with 4 electrons in the valence band, and we add a pentavalent impurity, let's say arsenic, to it through doping process. Okay, the process of addition of impurity to pure semiconductors or intrinsic semiconductors is called as doping. So when we add a pentavalent impurity to an intrinsic silicon, what happens? These 4 electrons out of these 5 valence electrons of the pentavalent impurity, 4, they enter into covalent bonds, okay, with the 4 outermost silicon valence electrons of silicon. So all these 4 electrons of silicon, they engage in covalent bonds with the pentavalent impurity. Now this extra electron, it gets left behind. Okay, this extra electron of the pentavalent impurity, it does not enter into any covalent bond because silicon has only 4 valence electrons. This pentavalent impurity, the 4 electron, these 4 electrons, they enter into covalent bonds, only this is left behind. So this extra electron, okay, this extra electron, it goes to the conduction band of the semiconductor, whichever one we are using for silicon, and that becomes a free electron and it is responsible for current conduction. Okay, so here electron negative charge is the majority charge carrier. That's why it is called as N-type semiconductor. Okay, because electron, which is a negative charge, that is the majority charge carrier, this extra electron, free electron from the pentavalent impurity. Now P-type semiconductor. So N-type is one which is doped with pentavalent impurity. A P-type semiconductor is formed when an intrinsic semiconductor, it is doped with a trivalent impurity. Trivalent impurities, they have 3 valence electrons, okay, 3 outermost valence electrons. Example, boron, gallium, indium, aluminium, etc. Suppose we dope an intrinsic silicon semiconductor with a trivalent impurity, let's say boron. So here in this case, these 3 valence electrons of the trivalent impurity, they enter into covalent bonds with, let's say, 3 out of 4 of these silicon intrinsic semiconductor. Okay, like this, 3 covalent bonds are formed between 3 of the outermost silicon electrons and 3 out of 3 of the trivalent impurity boron. Now here an extra space is created, okay, here between boron, which has no outermost electron, whereas silicon, which has 4 valence electrons. So this vacant space, okay, this vacancy for an electron, a spot, a free spot for an electron, that is called as hole. This vacancy created in the bonding process between boron, which has no more outer electrons, whereas silicon, which has 4 electrons, okay. So this vacancy is called as hole. Actually, hole is a hypothetical concept. This spot is filled, almost instantly by a surrounding electron, and then from where the electron comes, there another vacancy is created. So like that it keeps on continuing. I have already discussed it in basic electronics as well as physics of semiconductor devices, that hole is a space, a spot which has a strong affinity for an electron to occupy that space. So when the hole is created, almost instantly an electron from any surroundings, it will come and occupy that spot. From where that electron will come, there another vacant spot will be created, okay. So that spot will be occupied by another electron, creating another hole where it was originally in that spot. So like that this process gets continued. So this hole is the majority charge carrier for p-type semiconductors. So an absence of negative charge, so here we say it is a positive charge like that sense, but hole is a hypothetical concept. So absence of an electron, negative electron, that gives us a positive charge like that. So that's why it is called as p-type semiconductor. Absence of negative charge, negative electron which is negative. So in that sense it is positive, or it is called as p-type semiconductors. But there is no such thing as a hole, okay. Its only meaning is that absence of an electron in that spot, okay. A vacant electron site is called as a hole. It is almost instantly occupied by a surrounding electron, thereby creating another vacant spot where it was originally. That spot is again filled by another electron, surrounding electron. It creates another vacant electronic site, like that it continues, okay. So this is about the semiconductors and their classification, okay. So we'll continue our discussion related to optoelectronics devices and systems, and we were discussing about the semiconductors and their application in the design of optoelectronics components, mainly sources and reductors, and how the properties of semiconductors, they affect the functioning of the optoelectronic sources and detectors. So for that we have to understand some basic concepts related to semiconductors. So previously we discussed about semiconductors and their classification. In this video we are going to discuss about the basic atomic structure of semiconductors. So whenever we talk about atomic structure, the basic reference that we take for understanding it is Bohr's atomic model. So it was given by Niels Bohr in 1913. So according to this model, it has certain postulates. First is then an atom, it consists of a positively charged nucleus, and around which the electrons, they revolve or they move around in certain well-defined designated orbits, circular paths. Okay, that is the first and most important point. Nucleus, it contains protons and neutrons. It is the center of the atom, consisting the positive and neutral parts, and the negatively charged electrons, they move around the nucleus in specific circular orbits at fixed distances or radius away from the nucleus. So here only the orbits of certain fixed radius they are allowed. It's not that the electrons can revolve around in random orbits, because each orbit has certain fixed amount of energy associated with it, and it is directly proportional to the radius of the orbit or the orbit number, principal quantum number, like that. And the larger the orbit, the greater is the energy associated with it. It is obvious because the energy associated with the orbit is directly proportional to its radius, so the orbit number. Okay, so as we go away from the nucleus, the the electron energy in those orbits, it goes on increasing. And let's say we want to find out the energy associated with an electron. So here if we go back to basic chemistry, where we take hydrogen atom as the reference, the energy is given by minus RH by 1 by n square, where RH is Rydberg constant and n is the principal quantum number. Okay, it is the energy of an electron in a particular orbit. Okay, taking into account reference the hydrogen atom. So here the difference between the energies of the initial and the final states, let's say we have an orbit, let's say in the we call it NF. Okay, the principal quantum number is NF. So the energy of the electron in that orbit is given by minus RH by 1 by NF square. And let's say the electron was initially in orbit I. So in that case, with principal quantum number Ni, the energy is minus RH into 1 by Ni square. So the difference between the two is this. The difference between the energies of these two orbits is this. RH into 1 by Ni square minus 1 by Nf square. So here the transition of electrons from a lower orbit to a higher orbit, it requires absorption of energy equal to the difference between these two levels. Okay, initial and final level. Suppose an electron wants to jump from a lower orbit to a higher orbit. So it has to be fed with a photon of frequency nu and the energy given by h nu, which matches this difference, this energy difference. Only then it will make the transition from a lower orbit to a higher orbit. Another important thing is that these orbits, they are designated by the as KLM orbits, first, second, third orbits, like that they are designated as KLM. So for the transition of an electron from a lower orbit to a higher orbit, energy has to be absorbed, it has to be fed to that electron, but when it goes to a higher orbit, it cannot remain in that state for an indefinite period of time. After a certain fixed interval of time, it drops back to its original state. So when it drops back to its original state, the same amount of energy, the difference between the two levels, that is released. Okay, so for transition of an electron from a lower orbit to a higher orbit, energy has to be fed to that electron, it is absorbed, but when it moves from a higher orbit to a lower orbit, energy is released. Okay, like that. Now, because of these transitions, it is very important when we'll discuss about the design of optoelectronic sources and optoelectronic detectors, where because in optoelectronics light is the main important component. So here the absorption and emission of photons of frequency or wavelength, everything comes into play in relation to the atomic structure of semiconductors. Okay, so this forms the basic principle, this transition of electrons from one orbit to another on the basis of emission and absorption of light photons of particular frequency and energy, that forms the basic principle of operation of optoelectronic sources and detectors. So it will, this frequency will determine in what wavelength range or what frequency range we can use a particular optoelectronic source or optoelectronic detector, in which region of the electromagnetic spectrum. That is dependent on the frequency range, wavelength range, isn't it? So that energy or frequency that decides in what region of the electromagnetic spectrum we can use a particular semiconductor optoelectronic device. So that depends on the energy difference between two levels, on the band gap energy. We have already discussed about valence band, conduction band, all that, but the difference between the energy levels of the valence band electrons and conduction band electrons, that and the frequency or energy required to make that transition from valence band to conduction band. So that makes the basic principle of operation of optoelectronic semiconductor devices. Okay, so here we have discussed about the basic atomic structure of semiconductors. Okay.